Okay, my name is Harshini. I'm a postdoc at IISER Pune. First of all, I'd like to start by thanking the organizers for giving me this opportunity and also for organizing this wonderful meeting. I'm going to be discussing some work that I did some time ago with Anne Becker at TU Dresden and David Lewitz, who's now at the University of Bonn. We started thinking about these things when all three of us were affiliated with the Max Planck Institute in Dresden. So, okay, I'll just skip the outline, we don't need it. We started being interested in some work that was going on in the quantum chaos group in TU Dresden, where they were looking at the chaotic dynamics for a map with SK. What this means is that you start with an initial position momentum of a particle, you iterate under a certain chaotic map. They took the standard map, but it can be anything you like. And you define a region of escape in the phase space. They chose a vertical strip. So after this iteration, you get a new P and Q, and if that lies in this region, the corresponding trajectory escapes from the system. So this has several interesting consequences classically as well as quantum mechanically when you quantize this map and the opening becomes a projector. We were interested in whether there is a quantum many-body analog of such a situation and what the consequences of that would be. If you want to know more about this kind of system, it's over here. Okay, so this is what we cooked up. So you have a chain of spin half particles, and you have this Hamiltonian, which is quantum chaotic in the sense that the many body people look at it as. So you have nearest neighbor couplings, you have a random disorder field, and you also have randomly placed disorders along the sides. Okay, so this system evolves, you drive it. You drive this under the Hamiltonians H1 and H2 for two half periods. And H1 and H2 are just two different parametric configurations of this Hamiltonian. You basically want to make it as complex as possible, remove every possible symmetry, and so on. Finally, our system that we are studying is obtained by projecting out the last site from the chain. So we choose a projector of this form, and as you can see, it acts like a measurement. If the last spin of the site points up, then you keep the spin. If the spin points down, then it's thrown out of the system. Okay, and you end up with the subunitary operator, this curly u, which is given by p times u, and this is how the system evolves. And as you can see that, yeah, okay, maybe I'll just talk about some of the consequences. I won't discuss all of these. I'll have time to just discuss the entanglement dynamics because as you can see here, there are two competing effects. This U, which is the drive, generates entanglement, and this projector destroys it. And you act this U, you repeatedly act this U on your initial wave function, which could be an entangled state or it could be a product state, and we see what the net effect is. Okay. You could also look at the level statistics of this curly U in the framework of random matrix theory. And since it's a non-normal matrix, you'd have exceptional points. There are a lot of things going on, but I'm just focusing on this one. Okay, so to understand entanglement entropy, we quantify it using the von Neumann entropy. So if you have a bipartite system, that is you divide your system into two, subsystem A and B, and you trace out one of the subsystems, you can calculate the entanglement entropy for the subsystem with this formula, which is the von Neumann entropy. If there is no projection and you are just driving under this unitary operator, the entanglement rises to the maximum possible value immediately because that Hamiltonian is so complex. And this time here is basically the number of applications of the projector each time. So you see that without the projector, okay, it just saturates to a final value, which can be, which is well known. But under the operation of this curly U, it deviates, of course, from the maximum possible value. It doesn't even go to the value of L minus 1 spins, which is what you would expect if you project one spin out of the system of a length L. You get some other final value, and we try to explain what is happening here and whether we can quantify this. To get a better understanding of what exactly is happening, we look at the entanglement entropy at each site of the spin chain. So if you have a chain of 20 spins, you can calculate, again, the entanglement entropy at each site, which is given by this. Okay, so yeah, as I mentioned here, the entanglement entropy for a maximally entangled state called the page value is given by this. And I've shown the page value for three different values of L, 20, 19, and 18, which are these broken lines. And for our system, which is again here I've considered a spin chain of length L. Once you project the last spin out of the system, you would expect it, of course, that the last spin is out, so it behaves as a spin chain of length L minus 1, which is 19. So far, so good. But then you see that the effect of this projector somehow propagates more than halfway along the chain. And we are trying to understand why this deviation occurs. Okay, and to understand why this happens, okay, we tried a lot of things, but the idea is we need a generic understanding of how correlations build up in the system, and we also need to understand how locality affects the dynamics in the system. So to this end, I'll introduce the concept of random unitary circuits. The basic idea is that if there was no projection, if there was just the drive, then your operator U could be modeled as a random matrix belonging to the circular unitary ensemble. Doesn't matter what it is. It is one of the random matrix classes which Floquet systems are usually modeled as. So what that full random matrix does is it would correlate or entangle all the spins in the chain. If we want to understand how entanglement grows between each spins, we break it down and we introduce just 2 cross 2 matrices which entangle only the nearest neighbor spins in one turn. So if this is your chain and these are two sides, this entangles two nearest neighbors, this entangles the next nearest neighbors, and so on, and this entangles these two, and that's how correlations build up. And it should be obvious from this that the way entanglement builds up in this kind of situation is a lot slower than if it was just a full random matrix. Okay, so we extend this notion to more general K local circuits. Okay, I'm considering here K equals 4 because that's what we'll need later. But the idea is that instead of entangling just the nearest neighbors, you also entangle 4 of the nearest neighbors in each step. So between one time step and the next, you entangle all 4 possible nearest neighbors, and entanglement grows. And entanglement grows faster as you increase K until K equals L, and you just get a full random matrix. Okay, so I brought this up because we tried a lot of things, and by every possible measure, it seemed to us, and we looked at a lot of measures, including mutual information and OTOCs and so on, that once the spin is projected out of the system, it becomes completely uncorrelated. It should have no effect on the rest of the system, but we see a very clear effect. But if we model this as this kind of go to the operator space and model the growth of entanglement in that space, we see that for K equals 4, the growth of entanglement fits perfectly with what is happening in our system. Okay, and I think, okay, I'll just leave it at that. So our basic idea is that if we have this kind of two competing effects in the system, one of entanglement growth and one of destruction, it would be useful to go to operator space and look at how locality and this general kind of correlation growth can be understood. Yeah, so thank you. Yes.
So if you go back to the slide which had the projector.
Yeah.
Yeah. So is curly U still unitary? Doesn't
No,
look like.
it's subunitary.
Okay.
Compared the results for the two local cases. Yeah, the previous to that, maybe the bigger one. No, this one.
Okay.
So because you're projecting out the last spin, you're left with a system of 19 spins in this
Yes.
case, right? Now, because of the monogamy of entanglement, I would have assumed that if you make a cut which is very close to the spin that you projected out,
Yeah.
there should be a bit more entanglement than what you would get for the purely unitary case, because simply because of the monogamy of entanglement. That doesn't seem to be the case here. Do you understand why?
I'm sorry, could you say that again?
So that doesn't seem to be the case here, right? Because your
Okay.
blue line is below the purple line.
Yeah, yeah.
So, and closer to the,
Yes.
if the cut is closer to the
Yeah.
end. So do you, I mean, this is sort of contrary to what I would have guessed simply from monogamy
Yes,
of entanglement.
exactly. I mean, it was contrary to a lot of other things we measured as well, and
So-
I really don't have any way
Okay.
of understanding it as
Okay.
yet.
Thanks.
So, I mean, when you look at the entanglement growth as a function of time, I mean, somehow it looks like in one or two steps it just jumps to the fully entangled state. And why is that? I mean, does it depend on the initial state?
No, it's the nature of the Hamiltonian that we've chosen. This is a very complex
For any initial state, this happens, is it?
Yes, it happens with any initial state, and yeah, we tried with just product states or just.
And even with the, but with your random unitary circuits also, this same thing happens or no?
I mean, yeah, with k equals 4. If it is this, of course, it grows slower.
Okay.
So k equal 2 would grow like this. And for our system, it's k equals 4. We don't know yet if, what kind of Hamiltonians would follow what kind of k. That's a thing we're pursuing. But yeah, this is a generalization of this random unitary circuit model that was proposed here.
Project this out, right? So we can also think in terms of number fluctuation in rest of the system, right? So somehow if you project it out, the chance of number fluctuation in the other part become less, right? Can that be the reason? Because you this particle spin, which I mean, okay, I'm thinking in terms of number. It could have
Right.
hopped to this subsystem. Now it's thrown out, right?
Yeah.
So that can it decrease because number fluctuation is related to the entanglement of it, right? Can it decrease this thing?
I'm not sure how. I don't see how that would happen, but maybe we can talk about it.
Sure.
Yeah, so no more questions? Okay, so let's thank the speaker.